Hi, I'm Shweta Mahajan from the Max Planck Institute for Informatics, and I'll be presenting our work Discover-then-Name, wherein we invert the typical paradigm of building concept bottleneck models by first discovering the concepts known to the model and then naming them. Image classification networks typically use a feature extractor followed by a linear classifier to make predictions, but are not interpretable. To bring interpretability, concept bottleneck models insert a concept bottleneck layer before the classifier, which first maps the features to human understandable concepts and then predicts using a sparse combination of them. Let's look at how the concept bottleneck layer is constructed. A typical approach in recent works is, for a given classification task, to query an LLM for task-relevant concept names, and then leverage vision language alignment from CLIP to learn to map to these concepts, to finally construct the concept bottleneck. In contrast, our work flips this paradigm. We use a generic task-agnostic dataset to first discover concepts known to the model, which gives us a set of unnamed concepts. We then use a large vocabulary to name these concepts, to form the concept bottleneck. Overall, our method does not require LLM queries. Additionally, a single concept bottleneck can be used for multiple downstream datasets and is an intuitive approach to identify the concepts known to the model. Let's now look at the first step, which is automated concept discovery, where you use a sparse autoencoder or SAE in short. The encoder learns to disentangle concepts by mapping the CLIP image features into a high-dimensional and sparse space of concepts using a linear transformation followed by ReLU. The decoder then combines the unit norm dictionary vectors weighted by the concept strengths to reconstruct the CLIP features. The SAE is trained using a combination of feature reconstruction objective and a sparsity constraint on the concepts. At the end of this step, we have learned a mapping to concepts, but without names assigned to them. In the next step, we name these concepts. For this, we take a large set of words and map them to the CLIP text embedding space. Then, we take each dictionary vector from the decoder in the concept discovery stage and find the CLIP text embedding closest to it. The word associated with this text embedding is assigned as the name of the concept corresponding to this dictionary vector. We do this for all the concepts. At the end, we have a concept bottleneck layer given by the SAE encoder, along with a name assigned to each concept. The concepts are consistent across multiple datasets when looking at the top activating images, and the assigned name is appropriate. Here are some more examples. Additionally, with a user study, we find the discovered concepts to be more semantically consistent than CLIP features, and that highly consistent concepts are assigned accurate names. Further, the vocabulary used can control the granularity of concept names. For example, both these concepts have been assigned to the same name, tree. However, a more appropriate name gets assigned when added to the vocabulary. Now that we have our concept bottleneck, we use it to construct a concept bottleneck model, which we call DN-CBM. Let's look at how it performs. In terms of classification performance, DN-CBM performs competitively to prior work. It also provides granular explanations for model decisions that are comparable to prior work, as well as class-level explanations. Finally, we find DN-CBM to be amenable to test time interventions. To show this, we train a classifier on the binary land bird versus water bird classification task using the waterbirds 100 dataset, where bird and background types are perfectly correlated during training. This correlation is removed in the test set in the so-called worst groups, so a model that relies on background features would perform poorly. After training, we prune the classifier to only use 5 concepts per class and manually classify them as being bird or non-bird concepts. Before intervention, as expected, we find a large drop in classification accuracy in the worst groups. However, keeping only the bird concept shows large gains in accuracy in these groups. And similarly, keeping only non-bird concepts shows large drop in performance, showing the effectiveness of such interventions with our DN-CBM. In summary, in this work, we propose an alternative means to construct concept bottlenecks and show that it can be effective. Thank you, and we hope to see you at the poster session.